Yeah, can you hear me?
Hi, Luan.
Sorry.
Ah, hi, hi,
Hello,
hi.
hello, hello.
Are
So
you,
we are going to start. Sorry, Professor Han. So we are going to start soon. Uh,
are you the chair for today?
yes, yes.
Yeah. If you can give me a couple of minutes because I'm already made a video and it's about 20
Okay,
minutes. So I'd like a
okay.
little bit introduce about the FIB Indonesia. So probably the young members in Indonesia will be attracted. So just 5 minutes and then you'll directly go into the video that I've prepared already.
Sure, no problem.
Okay.
Let's do like that.
Yeah, that should be enough because I tried to make it not too long because you said 30 minutes, so I made it's around
Okay,
20. You're
okay.
you're looking great. You're looking great.
Yeah.
Yeah.
Thank you.
It has been a stressful time.
Yeah. So I
Professor
think.
Han, today you are very beautiful too.
I'm always very beautiful, Yanni.
Yeah. Sure. I agree. I agree.
But Yanni also looks very nice. Hi, Yanni. Good
Thank you very
morning.
much, sister.
Uh, you have a beautiful scarf and a very nice blouse. So I think you look great.
Yeah, I'm online from Jogja today.
Oh,
I'm not in
okay.
Surabaya. Yes, because yesterday I have a meeting with the ministry, so I have to go to Jogja. So I'm still in Jogja, not in Surabaya. I hope
I'm
everything
already
will be fine.
vaccinated, so I feel a little bit safer now.
Oh, congratulations!
Yeah. What happened with your university? Because this is held by my university, so the rector arranged that everybody will be vaccinated this week.
The professor got first, and
Oh, the
then
professor.
after
Okay.
that, the
That's why you should become professor soon.
I hope. Thank you.
Okay. So shall we start? Mm.
Yes,
Uh,
sure.
yeah. So can I speak now? So
Yes.
for to the
Yes.
all of the audience. Okay, dear friends, dear colleagues. So we are going to start the second day of the seminar. The JSCE MCA, the host, the recent advances and the practices of concrete materials, structures, and constructions in Indonesia, Japan, and Mongolia. So thank you all so much for your participating for this seminar. So as you may see in our schedule today, we have 4 speakers from Indonesia, Japan. Yeah. So I would like to first invite Professor Han Lee from Diponegoro University, Indonesia, and uh, she will speak about the external reinforcement technique using FRP, and she will also introduce about FIB Indonesia. So before that, I would like to first introduce her. So let me share her introduction slides. As you can see here, so she's now the professor of the University of the Deep Negro University, and also she's the chairwoman of FIB Indonesia. She got her doctorate degree from Deep Negro University and master degree from Canada and bachelor degree from Deep Negro University, and her expertise includes the graded concrete, fiber reinforced plastics for concrete, retrofitting and external reinforcing, modeling, and finiment element analysis. And yeah, he has a lot of papers, and she has a lot of papers, and her projects include the dynamic response of CFRP reinforced members with Taiwan and Japan. And she also has the self-compacting the geopolymer concrete for house members in the project. So Professor Han, so could you start to introduce the FIB Indonesia and your topic today? Could you please?
Thank
Your
you
time
very
is
much.
yeah, your
Thank you very
time is
much.
30
Yeah.
minutes. Yeah.
Okay,
please.
thank you very much,
Hi, Rose.
Dr. Luan. It's been a pleasure to be here with you. Actually, I already prepared the video. So after this, Dr. Luan will show you the video of my presentation. But I'd like to have a little bit time because at present, I'm the president of the FIB Indonesia, which actually is supported by the FIB International in Europe. And what I want to say is that like Dr. Fadila yesterday, she is one of our young members. So we're now opening the possibility for young engineers to join the FIB as young engineers. And I'm very, very happy to see that exactly these young engineers are doing a lot more than us. Yani and me, we're older. Yani is a lot younger than I, Dr. Januarti. But still, I'm very pleased that Dr. Fadila and the group of young engineers are doing so well. So everybody in Indonesia, if you're a young engineer, just try to join and do something for the concrete community. We can do a lot. I'm sure of that. And it's a very fun condition. I'm also very grateful for this opportunity, Dr. Luan. I met Dr. Luan before the COVID. We had a good meal together. So hopefully we can create bridges between nations, between friends, and that with that we can create something for the future. That would be it, Dr. Luan. So then maybe you can now go on with, I'll be attending all the time. And of course, for the question and answer, I will be attending live. So you can now put the film on. Thank you.
Okay, thank you. So we would like first to show the
Good
film
morning
from.
and welcome. My name is Han Aili and I'm a lecturer at the Diponegoro University in Semarang, Indonesia. I'm very happy to meet you all, and today I'm going to talk about external reinforcement using carbon reinforced polymers. This has been a product of our research from 2017 till now. So let's watch the presentation. External reinforcement techniques using FRP. Let's go to the philosophy first. Why do we need external reinforcement? In 2004, Aceh was hit by a mega tsunami, and it was followed by a series of earthquakes in Java, Lombok, and Gorontalo. The disaster took thousands of lives and resulted in a huge financial loss. So this will force us to modify the design criteria in Indonesia. What is the main idea behind this change? Firstly, it is the increase in the PGA, the peak ground acceleration, due to the zonation of the earthquakes in Indonesia. And the second is an increase in an 80 to 100% of the static equivalent lateral forces applied on a structure. So let's see Surabaya. Within the circle, we have Surabaya according to the code 2002. Here we have a PGA of 0.1 Gauge. Now let's look at the code 2019. Again, Surabaya now has a PGA of 0.4 Gauge. So this increase will substantially change the earthquake force acting on the structure. So we have a problem. What is our problem? Now, all concrete structures that were designed based on the older codes do not meet the new design criteria anymore. We cannot all demolish them and build new ones. So our solution is, let's do external reinforcement and let's do retrofitting to revitalize the structures who has cracked but who did not collapse yet. So this is our action plan. We will increase the capacity of a concrete member with external reinforcement using FRP. External reinforcement can increase the capacity through the flexure increase, through shear increase, or by using the concept of confinement of compressive concrete. We also can do retrofitting for cracked but non-collapsed structures. So this is the experimental simulation we did in the lab. Let's look at the structure, typical beam column joint. Here we will have gravity loads acting on the beam, like you see here. And then additionally, we will have seismic loads acting on the beam. As a result of these two, we will have a design load that will increase due to the increase of the seismic loads. The beam column joint is the area with the largest bending moment and the largest shear forces. So let's go to the lab. What actually happened, we see on the left. So we have a beam with the situation of the column, very large moments and very large shear stresses. So what we did in the lab, we put the beam upside down and applied 1-point loading at the center. So we still have a very large moment with a very large shear load. These are the section details that we tested at the laboratory. The green one is the beam designed during the old code. We only have conventional steel reinforcement, and now we will additionally reinforce the structure in flexure, the red ones, which can be wraps, it can be a plate, it can be a rod or a string, and we also did reinforcement for shear around the beam in the blue color. So this is what we have, and we tested it in the laboratory. Here you can see the full-scale beam ready for testing. You can see the shear reinforcement, and you can see the load applied at the center point of the beam. These are the FRPs that we used for our reinforcement. We have the wrap that looks like a sheet. We have a rod, we have a string, and we have a plate. The interesting part is that they all come from the same fibers like you see in the string. So they're all the same, it looks like hair. You can clearly see it in the wrap. So they are woven in a sheet, but for the plate and the rod, they are already pultruded and impregnated in the epoxy. So we have a couple of systems. Let's look at it further. We have the EBR, that is externally bonded reinforcement. Here the FRP will be placed outside the concrete, just attached to the concrete surface. We have NSM, which is near surface mounted. Here we will have to cut a hole in the concrete to put in the FRP and close the hole with the epoxy. So these are two entirely different systems. We can see the wrap and the plate are externally bounded outside, but the string and the rod are implanted or embedded into the concrete. For the system, we have pre-impregnated and pultruded, we call it pre-preg, which means that the fibers, like you saw before, were impregnated and pultruded in the firm, but with wet layup, we do it on site. You can see that for the wrap and the string, they were impregnated on site, but for the rod and the plate, it was fabric made. So that's why they were much stiffer than this wrap and the string when they arrived on site. So our issues, what do we have? During the test, we saw that debonding occurred. We also had the problem for the NSM that the concrete cover was not thick enough to fulfill the ACI codes. So what would we do about it? For the debonding, we proposed an additional surface treatment by putting grooves in the surface of the concrete, like you can see, we tested 4 types. And as a result of this, you can see that the factory treatment resulted in the bonding of the ITC between the FRP and the concrete, but for all our treated surfaces, the concrete failed. Okay, now for the cover problem, the ACI 440 mandated a 1.5 diameter embedment depth. As you can see, that's the right one on top. But if you have not enough concrete cover, you can only plant it or embed it probably for half a diameter. So we tested the impact of these 2 cases and evaluated the results. So now we can go to the results. We also have a retrofit and an externally reinforced member. Here we have the cracked beam, which did not collapse. First, you straighten the beam so that it's in the right position. You do a surface preparation by cleaning the cracks, cleaning the surface, and then we did an epoxy injection within the cracks. This is thanks to Sika, who has been supporting our research all year long. Okay, I will introduce you with 3 modes of failure that we encountered. The first one is denoted with a D. D stands for the bonding in the CFRP, and R is for rupture of the CFRP, and finally I have C, which is failure of the concrete. Now let's see the results. Here we have the externally bounded reinforcement wrap. You can clearly see that there is the bonding between the wrap and the concrete. This also occurred for the rod, which was near surface mounted, so you can still see the hole where it was planted, but still it came out, so we have the bonding. And for the plate, we also have the bonding in the ITC. As for the other samples, we then increase the performance of the surface to increase the bond. And now you can see that the FRP wrap was ruptured. This also happened with the string. You can clearly see that the string was broken. And only for the rod that was embedded in accordance to the ACI code, we had concrete failure. Let's now look at the results. Here on the left, we have the result of the control beam in red. We normalized it to the normal beam so that we directly can see the increase in capacity. The gray one is the wrap that underwent debonding. Still, you can see that there was a substantial increase of 47% to the normal beam. Then, with additional surface treatment, we had an increase of 62%, which is quite large. If you have a crack beam and you do retrofitting and then add the wraps as reinforcement and apply the surface treatment, then you'll have a 34 increase in moment capacity. So that means that even cracked sections do not need to demolish anymore. We can repair them and they still will have a substantial amount of capacity in their member. The best one, of course, is the rod, which was fully embedded according to the ACI 440. That will have an increase of 88% to the normal beam. The half embedded rod still was good enough for a 40%, but this one resulted in debonding. That's why a D is designated for the failure mode. And the string and the plate who ruptured and debonded both had an increase of 68 and 65%. So now let's look at the load deformation behavior. Here you can see the red one, that is the control element. It's substantially lower than all the other reinforcements. You can see that there is a huge increase in both capacity and ductility, you might see the string and the plate. These do not look that good, but in reality, something else happened. So I'll show you in the next slide. For the string and the plate, we had stress redistribution. So what happened, because we were using 2 strings and 2 plates, they did not fail at the same moment. So you can see all the way the load went up, and then the first string ruptured in the blue circle, and it went down, but then the beam underwent redistribution of stresses. The load was divided to the other string, and finally the second string ruptured. So if you can see the end result, still there was a substantial ductility improvement. So now let's look at the remarks. What can I tell you from our 4-5-year research? All the CFRP reinforcement resulted in a minimum 40% increase in capacity, so it's good. The full embedded rod, according to the 441 ACI, is the best. It almost increased the capacity twice if you compare it to the control element. And also, proper surface treatment will improve the load carrying capacity around 15%. Further, general comments. The rods and the strings require less field preparation. They also produce less dust and less noise disturbance. They also reduce the epoxy use required to attach the rods and the strings to the concrete. On the other hand, the strings and the wraps are flexible, so we could easily let them follow the trajectory of the member. The NSM method is very sensitive to the embedment depth, and additional surface treatment for the EBR will improve the performance. The ductility criteria needs adjustment since we could see that there was stress redistribution, especially for the plate and the string. Future research, we're still working on this. We haven't tested the dynamic or the cyclic loading. We haven't tested the loading-unloading protocol. At the time now, this is conducted in cooperation with the NCRE in Taiwan, Tainan. So this is what I show you. This is an international joint research between many parts, of course, supported by SICA. We have the Atmajaya University in Yogyakarta, the Nihon University in Japan. We also have the UNSUT in Purwokerto, the Diponegoro University, the National United University Taiwan, the Sengkung University, and of course the NCRE. So now we are going to test all these beams dynamically and under the loading-unloading protocol. I show you some pictures of what is going on now in Taiwan. So this is the loading protocol. Of course, you have to change the whole setup because now it will go 2-directionally, and you need an actuator to do this test. Let's go further on. What happens is, this is the NCRE, the National Center for Earthquake Research in Tainan, Taiwan. Here the beams are going to be casted. We are all very sorry, all the partners, that we couldn't travel to Taiwan to be there, but online also will work, and also it is our contribution. And then we can see on the next stage, here is the pouring of the concrete in the cast. Very neatly done. They dare not have a protocol anymore. They don't wear masks, all of them. And then finally, you can see here are the members ready for external reinforcement. You can see that the grooves are being made to put in the rods and the strings. This is our team in Taiwan. Next one. The effect of the anchorage to the confinement is being tested in the Diponegoro University this year. This will be a cooperation between the Diponegoro, the Atmajaya University, the Nihon University in Japan, the Sengkung University in Taiwan, and supported by SICA. So what are we going to do here? We are going to enhance the concrete strength through confinement. So we need over-reinforced beam. This is still a concept. We're going to do this year. And this is the proposed anchorage method because we found the bonding of the shear reinforcement. We will insert a fan into the concrete. So the end of the string will be put into the concrete and the outer part will be fan shaped and attached to the FRP using epoxy. This is our first scheme. The next scheme is that we will do an insertion. So we will cut a hole into the concrete. We will fold the FRP wrap into the concrete and fill the hole with epoxy. So this is what we are going to do this year, hopefully at the Diponegoro University as part of a joint research. This is a testing method because now we want to test the confinement. So now we are using a 2-point loading to create a pure bending condition between the 2-point loads. So this is entirely different. We will do a new scheme. And let me introduce you to our team. This is a joint research team of 2019. You can see everybody here together. And on the next slide, this is our team in Tainan, Taiwan. Very cool. So we can do it. We will do it. We will do research despite all those COVID things. Thank you very much for everything. And this is my family, my husband and my son who's doing his PhD and our beloved cat. Thank you very much, everybody, and I hope that you enjoy this presentation. Have a good day.
Thank you. Thank you, Professor Han. Very nice presentation, and we learned a lot from the about the FRP. Okay, so finally today we will have a session for question and answers. So and we already in the charting we sent you all our participants. You can fill your questions. You can ask questions by filling the form. That okay? So Professor Han, we will finally ask a question from the form. Okay. Thank you. So then shall we go to the next the presentation from Dr. Yasutaka Sagawa from Kyushu University, Japan. Professor Sagawa, so are you available, right?
Okay, good afternoon.
Yes. So I would like to sorry. So I would like to show the slide. The series slide. Sorry. Sorry, just please wait a second. Okay, apologize for the late show. So can you all see the slides? I would like to introduce Professor Yasutaka Sagawa. So you can see from the slides. So he is now the associate professor of the Department of Civil and Structural Engineering, Kyushu University. He got his doctorate degree, master degree, and bachelor degree all from Kyushu University. And his expertise is utilization of byproducts for concrete materials such as blast furnace slag, recycled concrete aggregates, and alkali silica reaction, ASR, and geopolymer. And his experience is he works in as an assistant professor from 2000 in Kyushu University, and then promoted to associate professor in 2010. And now today this topic is recent guidelines and technical recommendations of mineral mixers in Japan. We hope that he give us very nice presentation. So please, Professor Sagawa.
Okay, thank you for kind introduction. I appreciate Dr. Luang and other committee members of this international seminar in Indonesia, Mongolia, and Japan. Okay, so I'd like to share my presentation. Can you see my slide? Okay. Okay, let's get started. So the title of my presentation is Recent Guidelines and Technical Recommendations of Mineral Admixtures in Japan. So in the year of 2018, September, JSCE Concrete Committee published 2 guidelines related mineral admixture. Today, I would like to explain background and important points of them. Okay, cement is essential material for a wide range of buildings, infrastructure, and transportation system, and any kind of structures. Cement also plays an important role for resilient societies and sustainable development. As you can see in the first figure, global cement production about 4 billion tons in 2018. Global cement production has continuously and significantly increased due to rising population and urbanization. There are several future predictions of cement production. So in the second figure, which is the data of IEA, International Energy Agency technology roadmap. So the cement production in 2050 will grow up to about 4.6 billion ton in the lower level and 5.1 billion ton in the higher level. Cement production is accompanied by the demand of much of energy and much of emissions of CO2 gas. Cement industry is the third largest industrial energy consumer, and its production accounts for up to 6 to 7% of global CO2 emissions. CO2 emissions in cement production is due to the physical and chemical process when converting limestone-based material into Portland cement. From the data of JCA, Japan Cement Association, CO2 emission of ordinary Portland cement is 765 kilogram CO2 per 1 ton cement in Japan. So, and 63% comes from chemical process, and 37% comes from energy related. For example, fossil fuel, combustion, and electricity. CO2 emission cannot be avoided even if the production process is optimized as much as possible. In 2018, IEA published the technology roadmap for low carbon transition in the cement industry. This report is based on the roadmap to achieve 2 degrees Celsius scenario. So 2 degrees Celsius scenario requires to reduce CO2 emissions by 24% compared to reference technology scenario. And beyond 2 degrees Celsius, very challenging scenario requires to increase about 45% reduction effort compared to 2 degrees Celsius scenario. In order to decrease the CO2 emission in the cement production, there are several ways. The first one is innovative technologies such as carbon capture, storage, and utilization. The second one is reduction of clinker to cement ratio. The third one is fuel switching from fossil fuel to the biomass fuel. The last one is thermal energy efficiency in the cement factory. So today, my presentation focuses on the second one, reduction of clinker to cement ratio. So this figure shows the clinker to cement ratio percentage of cement types in Japan and the European standard. Clinker to cement ratio is defined as mass ratio of cement clinker to cementitious material. In other words, 100% means almost pure Portland cement. And 0% means without cement clinker. JIS standard, Japanese industrial standard, has already have specifications for slag, cement, and fly ash cement. OPC is ordinary Portland cement, can be allowed to mix small amount of additional materials such as blast furnace slag, silicate material, fly ash, and limestone. These materials can be mixed less than 5% for OPC cement. Slag cement is classified into 3 classes, Class A, B, and C. Class A is from the replacement ratio from 5% to 30%. Class B is 30 to 60%, and Class C is 60 to 70%. In the same way, fly ash cement is also categorized 3 classes. In 2018, JSCE Concrete Committee published 2 guidelines in the slide related to low carbon cement-based materials. The first one is Concrete Library 151. It is related to concrete with ground granulated blast furnace slag. Main target is Class B and Class C slag cement and equivalent levels. And Concrete Library 152 is a novel guideline, and it deals with concrete including high volume of mineral admixtures, such as blast furnace slag, fly ash, and other materials. So the content of mineral admixture is higher than 70%. So I was a committee member for both guidelines, but I'm afraid that these guidelines are not translated into English. Today, I'd like to introduce basic information. This graph shows the ternary blending of ratio of OPC, and blast furnace slag and other mineral admixtures. So the point A is ordinary Portland cement, 100% cement clinker. Yellow line means slag cement, class B and class C. So in other words, this area is the mixture of OPC and slag only. Orange line means a fly ash cement. So there are two methods to use mineral admixtures. One of the premix type cement, such as slag cement and fly ash cement. The other one is the material mixing at the concrete mixing plant. In the second method, the user can choose replacement ratio, but the mixing plant needs to have the silo of mineral admixtures and other facilities. But both methods can be considered to be equivalent from the viewpoint of hardened concrete properties, such as strength and durability. So the title of Concrete Library 151 is Recommendations for Design and Construction of Concrete Using Ground Granulated Blast Furnace Slag. Slag cement in Japan has over 100 years history. In JSCE Association, the first guideline of slag cement concrete was published in 1988. The second edition is published in 1996. So the current version is this one, Concrete Library 151. The target of this guideline is slag cement class B and class C. Class B and class C and equivalent level. So you can mix the blast furnace slag in the mixing plant. So the title of Concrete Library 152 is Recommendations for Design and Construction of Concrete Structures Containing High Volume Mineral Admixtures. So in this guideline, the target is pink colored area. The content of OPC is less than 30%. And also the percentage of blast furnace slag is larger than 50%. There have been many data in laboratories and actual applications by committee members. So some people may know alkali activated materials, AAM, and geopolymer concrete. So, but this guideline does not include these materials, AAM and geopolymer. Since 2019, new subcommittee has established to discuss geopolymer concrete. It has just started to discuss the property of geopolymer concrete. Okay, why do we focus on the concrete with high volume mineral admixture concrete? Now, as you know, concrete consists of cement, water, aggregates, and other materials. CO2 emissions of concrete is about 250 to 280 kilograms per 1 cubic meter concrete. And almost of them comes from manufacturing from OPC. Manufacturing OPC. Concrete with mineral admixtures have well-known and effective measure to reduce CO2 emissions and to contribute to reduce environmental impact in concrete sector. However, so in Japan, the use of mineral admixtures has not been expanded. So, but there are so many advantages by using mineral admixtures. Utilization of byproducts and protection of natural resources, low heat of mass concrete, reducing salt damage and ASR. Okay, so from this background and current situations in Japan, JSCE committee published two guidelines. The first one is related to ground granulated blast furnace slag. It includes recent investigations and experimental results. And the other one is new guideline of concrete with high volume mineral admixture. So the high volume mineral admixture at an exceeding JIS blended cement level. So it can contribute to the solutions for low carbon concrete. So I would like to share the information about the JIS standard related to blast furnace slag. Molten slag is byproducts in steel making process. As you know, blast furnace slag is byproduct, but it was a very precious material for concrete technology. So when molten slag is rapidly cooled by water jet, granulated blast furnace slag is generated. It is similar to sand. In the JSA 1511 Part 1 specified slag aggregate, not only slag sand and slag coarse aggregate. Slag coarse aggregate is produced by a slowly cooled and crushed process. So when the granulated blast furnace slag is crushed and grounded into fine powder, ground granulated blast furnace slag GGBFS is produced. It is very fine powder. In JIS standard, there are four types. So 3,000, 4,000, 6,000, and 8,000 square centimeter per gram of specific surface area. 4,000 is a very common type for concrete material, and 3,000 type is specialized for mass concrete to reduce hydration heat of concrete. And 6,000 is used for pre-stressed concrete or precast concrete to increase initial strength of concrete. And 8,000 grade is very special use, for example, aesthetic precast panel and so on. After mixing OPC and ground granulated blast furnace slag, this is a slag cement. So as I said, there are three classes, class A, B, and C. We have the standard in JIS specifications. So I'd like to explain important points in Concrete Library 151. The latest information is include and expressions of codes and commentaries are unified with JSCE standard specification. It is performance-based design. And not only Class B level, but also slag cement C, Class C level is mentioned. There are information about the concrete with grade 3000 for mass concrete and 6000 grade concrete for precast concrete and pressless concrete. So, interesting point is verification of carbonation. So from the latest version of JSCE standard 2017, the water penetration rate is available for the verification of steel bar corrosion due to carbonation. So, but conventional methods using square root T equation is also available. Generally, the speed of carbonation of slag concrete is faster than that of OPC concrete. But the recent researches have showed the difference of carbonation rate and slag concrete from OPC concrete is very small. So the coefficient K can be chosen from the value of 0.7 to 1.0. So, and new premix type slag cement is mentioned. For example, low heat and low shrinkage type cement and high volume and low shrinkage type cement. So this slide shows the application of Class C slag cement for foundation project, foundation extension project in a steelmaking factory in 2018. The CO2 emission of this concrete, sorry, in Japanese. So this is right side is normal concrete. It is about 240 kilogram CO2 emissions, but this new concrete Class C concrete reached to lower than 100 kilogram CO2 emission. So it means reduction by 60%. The other application is GGBFS 6000 for PC girders, pressless concrete girders. So in this application, high early strength Portland cement 50% and slag 50% is used. So in this case, some strain gauge is introduced to measure the shrinkage for monitoring. So the girders consist of some precast segments. They are transported from the factory into construction site, and then they are connected by post-tension method. So it is a two-span bridge. So this bridge opened 2019 March. So yesterday I just visited this bridge to check the monitoring condition. So we continue the monitoring of strains of concrete and temperature. Okay, the last part of my presentation is concrete library 152 related the concrete high volume admixtures high volume mineral admixture. In this guideline, the definition, it is a new guideline. It is based on the collaborative researches with PWRI, Public Works Research Institute, and construction companies and related associations during 2011 to 2015. And so it is based on the not only laboratory-based experimental data and exposure, but also exposure test shown in this slide. So there are so many specimens. So in the exposure site in the mild climate and cold and tidal zone and subtropical and tidal zone. There are so many patterns of combination of materials. In this guideline, the definition of high volume admixture is given in the following equations. The first one is the ratio of mineral admixtures to the total binder. It means cement plus mineral admixture should be larger than 70%. And the content of slag in the admixtures is larger than 50%. So it is a definition of high volume admixture concrete in this guideline. So in this guideline, the mineral admixture are categorized into blast furnace slag, fly ash, silica fume, and expansive additives and other materials. Other materials consist of gypsum, slaked lime, and limestone powder. From the Portland cement, which is ordinary Portland cement or high early strength Portland cement, to slaked lime, it is calcium hydroxide. It is categorized as binder. So you calculate water to binder ratio, W by B. You can include these materials. So they have chemical reactivity in concrete. So I'd like to show some data relating durability of high volume admixture concrete. So left figure shows exposure test result of carbonation. So the vertical axis means the carbonation rate in the natural environment condition. In scuba, it is mild environment. White color means normal concrete by using ordinary Portland cement or high early strength Portland cement. Orange color means high volume mineral admixtures. So you can find the larger carbonation rate for the high volume mineral admixture. So, but we can modify the mixture, for example, reducing water to binder ratio. Right figures show the result of chloride ingress into concrete by laboratory immersion test. So the test period is until 2 years. The upper graph shows the normal Portland cement, and the lower figure shows the result of high HPC cement and blast furnace slag 85% and gypsum 5%. So in this test, the liquid for the immersion is 10% sodium chloride solution. So as you can see, the speed of chloride ingress is smaller for the lower graph. And you can understand the mineral admixture can improve the resistance against chloride ingress and salt damage. Okay, so I'd like to show some applications of concrete with high volume admixtures, but I don't have enough time. So please look at the first line. It is the information about the mixture and the water to binder ratio. So the first application is foundation of mega solar power plant. The concrete have the OPC 25% as blast furnace slag 75%, and the water to binder ratio is 37%. Next application is for foundation of machine. It is mixture of HPC and BFS. And the next application is ternary blended binder, HPC and blast furnace slag and fly ash of 25%, 45%, and 30%. It is ternary blended. So the last example is very challenging case compared to ordinary cement concrete because it is a concrete without Portland cement. No Portland cement is used. 77% blast furnace slag, 7% of expansive additives, and 7% of calcium hydroxide, and 9% of limestone powder. Calcium hydroxide is performed as an activator of blast furnace slag. So I want to conclude my presentation. Today, I talk about the background and the motivation for low carbon concrete and the recent activities in JSCE committee. One of the solutions, to reduce CO2 emissions of cement is to increase the content of mineral admixture in concrete. So yes, we can understand this philosophy. But there are so many obstacles and difficulties, and each country and each place has a different material supply chain and different material standards. So what I want to say is that it is very important to work together and to study advantages and disadvantages for these materials, and to share knowledge and exchange information widely, not only national-wide, but also worldwide. So I believe that we can solve the big question for the sustainable development. That's all for my presentation. Thank you for your kind attention.
Thank you. Thank you, Dr. Sagawa, for your nice presentation. From your presentation, we know the recent advances in the mineral admixtures in Japan, and I hope that will also help the work in Indonesia and Mongolia. Okay, so
Yes,
thank you, and we will finally collect the questions and ask you in the question sessions. So thank you.
Okay, see you soon.
See you soon. And then we will move to the next speakers. Dr. Yani, my good friend. So she's from ITS Indonesia, and she will give us a very nice presentation about the combination of microbes, fly ash, and bottom ash for high volume coal ash concrete. Okay, so I would like first share the CV or introduce her. Can you see me? Can you see the slide,
Yes.
Dr. Yan?
Yes.
Yeah,
you can see
so
that.
as you can see, yeah, so I think many the audience are familiar with you, I think, right? Yeah, so she now works in the ITS. I know she also is a director of Indonesian Polymer. So she's an expert in geopolymer. So she got her doctorate degree from the University of Tokyo, and her master degree from Institute. This is in Indonesia, Bandung, the Technology Institute, both the master and the bachelor degrees. And her expertise include green concrete, waste materials, and concrete durability. And her experience, she worked in the World Bank as a World Bank, the consultant in the between 2002 to 2004, and she was also works as a lecturer of the University Islam Indonesia in 2000 to 2002. And she got 7 patents, and 1 patent has been granted. And for awards, as you can see, she has already got a lot of awards, like best researchers in Indonesia, and the first prize of the mining and the minerals industry institute research award, and the chairman the discrimination the silver awards. Yeah, so we would like to welcome Dr. Yani to give us the presentation. So please, the 30 minutes, I will let you know that after 20 minutes.
Okay. Thank you very much, Luasa, my best friend. Thank you for introducing me. Okay, I will share my presentations today. Okay, can you see that?
Yeah, we can see.
Okay, so I will make it bigger.
Yeah.
Okay. Good afternoon, everyone. On behalf of the host.
It's now it's in the show mode. So before that, it was not in the show mode. Yeah, it's okay now. No problem.
Okay. No problem. Okay.
No problem.
Okay. Okay. On behalf of the host event, I would like to thank to every participant who is still enthusiastic to join us in the second day. My name is Januarti from ITS Surabaya, as introduced by Luangsan. Today, I will share my experience on using bacteria in concrete mixtures containing high volume fly ash. Include biomass. Let's see the recent data of Indonesian government's plan in 2020 to 2024 to increase the national energy supply. There was a target to reach 35 gigawatt. It implicated the compositions of the source, as it is easier to use coal-fired power plant here. Then the power plant ratio has increased from 53% in 2015 to more than 80% in 2024. So of course, this makes another problem on coal ash management. On the other hand, the government is increasing also the infrastructure, especially in transportation field, the left side, to make more connections between cities. And this has to be correlated to manage the cost on maintenance, of course. as Professor Nakamura explained yesterday, we have to spend more attention to maintain our infrastructures during their service life. So it is not cheap because every year it costs around 1.5% from its construction cost. Actually, we have also another problem. It's also explained by Sagawa Sensei. The problem on the environment, as reported in 2018 by Ministry of Environment and Forestry, the total emission is dominated by changing the land functions from the cropland to non-cropland to cropland. So it means that we change the function of the land. And we have also a problem on peat decompositions and peat fire. And from the energy sector here, the right side, yeah, it also contributes more because of activity from coal-fired power plant. And finally, the left side in the bottom, in the cement sector, cement productions contributed more than half emissions in industry sector. As we can see, the increasing of cement production in line with the increasing of national infrastructure plan. Here, we face some problems to be solved. We must decrease the emissions and consider the environmental problem. In concrete industry sector, sometimes using river sand is not recommended because of instability of river in some places. As we are in the tropical country and have a very long coastal line, of course, durability and hot concreting are also the additional problems. Then let me show you our experience to utilize collage as much as possible to solve this problem. We increase the utilization of fly ash in concrete as a cement replacement, as a cement substitution up to 50% by cement weight. It is not as much as Sagawa Sensei's explanation before, but we have done our best. It has a positive and negative effect to the concrete. It increases the strength at the later age. It has also lowered the porosity and decreased the temperature hydration. However, as a pozzolan, it has a lower strength at the early age and contribute to high shrinkage and makes the workability lower if we use more than 30% by cement weight. We also use bottom ash as a sand replacement up to 25% to get its property on internal curing in the concrete. But of course, it has negative effect to the concrete, very similar to fly ash. And we know that it is a porous material, so it must affect to the higher shrinkage in the concrete. Then we have to find the solutions. We have to find the antidote for the collage effect. So we use microbes in the mixture. In our most experiments, we use Sporosarcina pasteurii as the bacteria for especially for concrete. And then we use these microbes, and also it is found that the microbes created gas as the metabolism product during the casting. So it increased the workability of the concrete during casting. However, it requires lower hydration temperature. So it is less effective actually in concrete if we put high cement content in our mixtures. At the end, our expectations here is having a lower cost concrete with lower porosity and lower hydration, and we have to see if it has a negative effect to the concrete properties. So this is, I have to emphasize here for the microbe selections. Obviously, we have to use non-pathogenic aerobic bacteria. We don't want to get sick because of this kind of bacteria. So it should be non-pathogenic bacteria. And it has to work to fill the pores if the oxygen exists. As concrete containing lime, the pH may a bit higher, and the microbes have to stand high alkalinity. So we isolated the bacteria from lime source, very local place in East Java. This is the reaction occur. I will show you the reactions. When we insert the microbes in the concrete, the carbon dioxide from bacteria can react with portlandite. Okay, there is also the ureatic enzyme, and it reacts with the portlandite to create calcium carbonate. So the calcium carbonate precipitated in the concrete pores to make the concrete becomes denser because it reduces the concrete pores. Okay, I will go to the next slide. We have found that some local bacteria in Indonesia can be very much useful to increase the concrete performance. We have Bacillus subtilis, and even we have also the Bacillus stephensis to produce calcite here. And also, even we can find aragonite in concrete pores. It is a very hard material and it's a very strong material. It fills the interfacial transition zones in concrete. So there is no gap between the aggregates and the concrete matrix. So we are lucky once during the SEM analysis, we have captured the binary fissions here, the binary fissions of the bacteria inside the concrete. We have also another innovations on using sodium hydroxide to increase the pH of concrete. So usually cement contribute to pH at 12.5 to 13 in concrete mixtures during the casting. By using fly ash and bottom ash, and bacteria may decrease the pH in concrete. So we use a very low concentration of sodium hydroxide of 0.03 molar to be introduced to during the casting, and also as the water substitutions. And it also increased the reactivity of fly ash. And this is, I have also the schematic simulations. This is the internal curing effect from bottom ash that we expect to occur during the hydration of the concrete. It works as a sponge. It absorbs water at the beginning to lower the water to cement ratio and maybe lower the workability. But then it releases moist gradually at the later age. So this is called internal curing. So it contributes the moist to guarantee the next chemical reactions because of the pozzolanic reaction and because of the bacterial activity. And this is a bit complicated, but I tried my best to make simulations. This is the schematic reactions during the first hydrations at the later age of the concrete using bacteria, sodium hydroxide, and the coal ash. And the bacteria produce the CO2, react with the portlandite to produce calcite, and also the fly ash react with the portlandite to produce new calcium silicate hydrate. And at the end, we have a denser concrete, and the bottom ash here still working to guarantee the internal curing inside the concrete during the hardening process. In the next slide, okay, sorry, okay. In the next slide, in our experiment, we used a mixed design to obtain the strength of 25 megapascal in 28 days. As a cement replacement, a class F of fly ash was used, and 40% and 50% by cement weight. And bottom ash was used to replace only 10% of standby weight, but it's actually quite a high amount. We made a certain sequence of mixing of the material during the casting. It is very important because it will affect the workability of concrete. We place fly ash first, then mix with the sodium hydroxide, and then continue with all aggregates, and followed by cement and superplasticizer, and also add water containing superplasticizer in the final mixtures, and also we put the bacteria. And also we make a different superplasticizer between the black here. Black is the non-bacterial concrete, and the red here containing bacterial, because yeah, we keep the bacterial inside the concrete in constant for about 400 milliliter per cubic meter of concrete. And because of the different workability using bacterial and non-bacterial concrete, we make a different content of superplasticizer. For non-bacterial concrete, we put 0.23 by binder weight, and we decrease the amount of the superplasticizer to only 0.1% by binder weight. And we made cylindrical specimen for the strength test and the shrinkage test. We also prepare the cubical specimen for monitoring the hydration temperature in 24 hours after casting. In total, we have 272 specimens, and this is the result. The slump of concrete is something very important to analyze, as the ash content increase in order to achieve good workability for the slump target at 10 centimeter to 14 centimeter. We add water. Yeah, at the end we add water in the mixture as the fly ash content increase. The ash indeed absorb water during the casting. As expected, bacteria increase the workability of the mixture. So we can see here, and the blue one here, the specimen containing 10% of blast furnace light. And this is the result of temperature monitoring during 24-hour hydrations. The ash helps a lot to decrease the temperature up to 13%. And something very interesting to see, I use my preview, I use my last experiment in Japan in the University of Tokyo to measure the shrinkage concrete for 10 days. And I put the embedded strain gauge in the center of the concrete, and we can monitor the shrinkage during the hydration of the concrete up to 10 days. As the ash content increase here, we add more water in the mixture, then the shrinkage increases too. But it is very much surprised to see that the specimen with only 30% fly ash and the specimen containing bottom ash show lower shrinkage than the normal concrete. This causes by the ash content and good compatibility and good compacting of the mixture during the casting. And this is also very interesting to see that if we do not control the slump, we just keep the water to cement ratio as it is, constant to our mixtures to guarantee the moist curing, and we have to guarantee the moist curing up to 10 days. We found that there is no difference of using 30%, 40%, and 50% fly ash as a cement replacement compared to the control specimens. And there is a report that using microbes in concrete here, the right side, doesn't affect the shrinkage. So it is there is no difference using bacteria or non-bacteria in the shrinkage measurement. For the compressive strength at the 28 days, as expected, concrete with the higher fly ash content has low compressive strength. However, at the later age, at 63 days, we found that the increasing rate of the strength is higher than the normal specimen. It is very much pleased to see that the effect of the internal curing by bottom mass worked very well as the effect of the bacteria to fill the concrete pores during the hydration. And as expected, because of the denser concrete pores, a higher split tensile strength shown by specimen containing bacteria and bottom ash can be shown here in this result. And if we analyze the microstructure of concrete, we found that at the later age, at the ash content increases, the pore becomes denser, so it reduces, yeah, the pores of the concrete. And especially if we have biomass incorporated with the microbes, we'll see the product of bacteria and role of the sodium hydroxide in the next slide. This one. Albite, as a product of aluminosilicate, react with the reaction product between sodium hydroxide and fly ash in the early age, increase as the fly ash presents in the mixtures. The product of bacteria was also found, as we can see that there is a calcium carbonate content in the result, especially with the red specimen containing bacteria. On the other hand, we can see that there is slightly decrease of portlandite as a product of cement hydrations. Why? Because it reacted with bacteria and silicate in fly ash to produce new calcium silicate hydrate and precipitated of calcium carbonate in the concrete pores. And finally, we compare the result of normal strength and higher compressive strength. We found that there is a decrease of CO2 emissions by 44% for all specimen using 50% collage in the mixtures. And the cost of material is also reduced to from 18 to 26%. And it is a very good contribution to the concrete ready mix industry to get the carbon credit actually. And finally, this is the conclusions. As we applied high volume collage in the mixture, we obtain many good results. Yeah, even though we have a slightly lower strength, we can manage that in the future research. We get a lower cost at least, and denser matrix, low hydration temperature, and better shrinkage. If we control the water content, is very much important. And of course, we can contribute to sustainable concrete. And Dr. Ruan, this is the end of my presentation. Thank you very much, and I go back to you. I will stop sharing my file.
Thank you, Dr. Yani. So very nice presentation using bacterial and fly ash and bottom ash. I think it's very promising for the further use in the practical material as practical material. So we have already see some question come to you in the form, but I will ask in the session, in the question session, and hope to you are waiting there for the.
See you later.
Okay, see you later. So then we move to the last speaker, Mr. Takeshi Torichigai from Kajima Corporation, Japan, and he will introduce the application of fly ash cement to concrete structures in Japan, mainly the dam construction case. So that will be very interesting topic. So I would like to, so are you available, Mr. Torichigai? Are you here? Excuse me. So, Mr. Torichigai, are you here? Can you hear me? Dr. Nia, can you hear me? I feel the no response.
Yes, I can hear you.
Okay, yeah. So I will first share his CV, and then I will check whether he's here. So I think that you can see his CV. This is his profile, Mr. Takeshi Torichigai, expert in the real construction. And he is now the senior research engineer in the concrete and construction materials group, Kajima Technical Research Institute, the Kajima Corporation. He got his master's degree and bachelor degree both from Kyushu University. And he expertise is ecological and green concrete, concrete durability, dam concrete. And his experience is he works in the dam, the Gokayama Dam in Fukuoka, Japan, as for the construction supervision in 2013 to 2016. And he has already got more than 10 patents granted in Japan. Okay, I think Mr. Torichigai is now here. So would you please to start your presentation? The time is yours, and I will the 30 minutes. I will remind you. Okay, please, Mr. Torichigai, for sharing your slides.
Okay. So I can't hear. Can you hear voice?
Yeah, we can
Okay.
hear.
So
We can hear.
Okay. Sorry for delay. And my name is Takeshi Torichiga from Kajima Corporation, and I will share my
Yes.
share my presentation sheet. Just a moment, please. So I'm a little bit nervous, so because of my poor English and final presenter.
Sure, no problem.
Take
Take your time.
Just a moment, please. Okay. Can you see it? Okay.
Yes, we can see it. No problem.
Okay. Okay. So Takeshi Torichiga from Kajima Corporation for Japan. I'm a senior research engineer of research section, Kajima Technical Research Institute, research section of my company. So today I'll talk about this title, application of fly cement to concrete structure in Japan, dam construction case. Just a moment, please. Okay. So, I'm glad to get the opportunity to give this presentation. This is a outline of my presentation. Firstly, let me introduce about my company, and next, construction method of dam, concrete dam. And third, how to use fly ash for dam concrete in Japan. And lastly, property of dam concrete using fly ash. Okay. So firstly, to introduce, I'd like to make a brief introduction of my company, Kajima Corporation. This slide shows the introduction. The headquarters of my company is Tokyo, Japan. My company's business fields are civil engineering construction and building construction, real estate development, design and engineering. This slide shows the history of my company. Kajima was established in 1840. My company's mission or policy is to lead the industry by constructing Japan's world's first. The figure shows the middle photo shows the Kasumigaseki building, that Japan's first skyscraper, and the right side photo shows the Tokyo International Airport, or the first hybrid structure. Next slide is fact of our companies. Paid-in capitals are over $814 million. And the revenue is a little bit old, but the revenue of my company is $18.4 billion. And employees 17,730. The Kajima, so that includes the national subsidiary and the international subsidiary, like this. And this slide shows the civil infrastructure that our company has constructed. Bridges, tunnels, dams, railways, seaports, and airports. And I have worked at dam site as a quality control manager of dam concrete for about 3 years. And our company is covering all phases of product. Ordinarily, the contractors only responsible for construction, I think. But our company joining in all phases, not only for construction, but also from the early planning and design to maintenance. Example, or the planning and development and designs and engineering and construction. That's the main aim of my company. And operational management and maintenance and renewal, like for all phases of products, of projects we done. And this slide shows a research field of Kajima Technical Research Institute. The background of researchers all cover a very wide range of research fields relating to civil and building engineering, such as material. I belong to this group. And structural engineering and environmental engineering, mechatronics, numerical analysis, chemistry, and animal and plants. Very, very wide fields, stuff, our company. Okay. Then, secondly, I talk about construction method of concrete dam. As shown in this photo, the dam is built to dam the flow of the river. So this is a river, and the black triangle shows where the dam is built. With a building dam, it's not possible to build a dam with water flowing. For this reason, we will dig a tunnel in the mountain and divert water through the tunnel to prevent water from flowing down construction site. This is called commutation. This is a commutation. This is a photo of the actual commutation work. A little bit small, but this is the name of the dam, Gokayama Dam. I walked at the site. The river originally flows in front of the photo like this. And the dam is built to the left side of this photo. And the commutation dig the tunnel to this way. Then, after changing the flow of the river, the next step is excavate the mountain. The soil and the soft rock on the surface are removed to expose hard rock. Once hard rock is exposed and before cleaning, and this photo shows after cleaning. It is ready to clean. It to be cleaned with river water, and concrete is ready to apply up to this hard rock. Okay. After the excavation is completed, the next step is concrete construction. Sorry. As for the concrete of the dam, the composition of the concrete is changed depending on the outer, where the surface is exposed, and the inner part, which is inside of the dam. For the outer part, it is used highly durable concrete. On the other hand, for inner part, concrete is used to reduce heat generation by reducing the amount of cement used as much as possible, and by using a large size of gravel. The maximum size of the gravel is about 80 millimeters or 150 millimeters. This slide shows the RCD. Just this slide shows the RCD, roller compacted dam concrete. RCD concrete is one of the concrete used for the inner part of the dam. It is applied to big size dam. RCD is as a first property of RCD is very hard. The slump of the RCD concrete is 0. Therefore, it is transported to the site by a dump truck, as shown in this photo. The water cement ratio of the dam concrete, RCD concrete, ordinary 65% to 80%, like this. The RCD concrete transported to the construction site. It's spread and leveled by the bulldozer. This photo shows the bulldozer, and this is the RCD concrete. The layer thickness of the spread level is determined to be 250 millimeters per layer. By repeating this work 4 times, the RCD concrete will be 1 meter high. 4 times and 1 meter high. After laying it with a bulldozer, after laying the RCD with a bulldozer to a height of 1 meter, the next step is to compact with. The next step is to compact RCD with vibrating roller. The number of compaction by the vibrating roller is determined conducting a test in advance. At our site, the compaction, the number of compaction is 12 per 1 lane. And the slump of the concrete used for the outer part, like this outer part of the surface is 3 centimeters. The slump is 3 centimeters. The water cement ratio of the concrete is ordinarily 45 to 55%. The concrete of outer part is transported by cable crane, and compacted with a large vibrator that is attached to heavy equipment. This is heavy equipment and attached with the vibrator. The maximum size of the gravel is 80 millimeter. Okay. Next, I will introduce how fly ash is used in dam concrete in Japan. This slide shows the quality standard of fly ash specified in Japanese Industrial Standard JIS that is mentioned before the presentation of Dr. Sagawa. Japanese Industrial Standard. The fly ash can be divided into 4 types in Japan. The numerical targets shown in this table are set to each type of fly ash. The item is such as SiO2, moisture, ignition loss, density, fineness, flow, and activity index. That is for 28 days and 91 days. The most popular fly ash in Japan is type 2. Here, we introduce example of detailed rules we're using fly ash for dam concrete in Japan. Detailed rules. This slide shows an example of dam construction specification document that used at my work site, Kokoyama Dam. 1. For fly ash quality, target value and fluctuation ranges must be set for the following items, like SiO2 and ignition loss and fineness. This is the target value of JIS standard. And at our site, the target value and the ranges are decided as you show. It is required to set the target value and its width and stricter regulation than the JIS standard is required for us. Therefore, construction company like our company and cement manufacturers are required to strictly control quality control. In addition, the following sentence were written in the dam construction specification document at my site. Second, contractors should use cement and other mixtures manufactured in the same factory until dam concrete is completed. But if the amount of fly ash used increase due to the rapid construction of dam, fly ash from one factory would be insufficient, we think. And third, the cement can be delivered to the site after making a pass or fail judgment based on the test result for 28 days compressive strength of cement. Due to the large amount of fly ash used per day, there is no place to store 18 days and 28 days of fly ash cement plant. In this way, we are trying to strictly control the quality of fly ash better than JIS. And concrete by establishing strict regulations. On the other hand, if the speed of the dam compressions is increased, it will not be possible to comply with these regulations. So the construction of concrete dams is proceeding while conducting various tests and changing the rules in consultation with ordering party. A few slides from them shows an example of a test conducted to modify the rules. We evaluated the effect of the location of fly ash A, B, C, D on the physical characteristics of concrete, the dam concrete. The physical characteristics of the 4 types of fly ash used for Gokayama Dam site A to B are shown in this table. There are some that have slightly different fineness and flow. A to B is different factory. This slide shows the particle size distribution of 4 types of fly ash A to D. JIS does not regulate the particle size distribution of fly ash. You can see the particle size of fly ash varies slightly depending on the type A to B. This slide shows an example of confirming the compressive strength of dam concrete using fly ash A to D. This test result was done at laboratory. The concrete used outer part of concrete, dam concrete. It was found that the type of fly ash used this time does not significantly affect the compressive strength of dam concrete. The dam concrete. Based on the test result, the dam was constructed with changing the production area of fly ash in consultation with the ordering party. This slide shows the usage of air-entrained agent used to dam concrete. In order to produce concrete with the same air content, it is necessary to control the amount of air-entrained AE agent every day. The amount of AE agent depends on quality of fly ash and the outside temperature, like this. So we control every day. We control the quality and fresh property of concrete every day, every hours, and changing the AE agent, and we conduct construction the concrete. Finally, the property of dam concrete finally. Okay. The property of dam concrete using fly ash I will introduce. A mixed proportion of dam concrete, outer part and inner part of the concrete. And inner part is divided into 2 types of concrete. One is LCD and one is slump concrete. Then the unit water volume of RCD concrete in the inner part is 101 kilogram per cubic meters. The amount of water is in RCD is very, very small, like this. The unit cement amount is 130 kilogram per cubic meters, and the cement called MF20. M shows the moderate heat potent cement, and F shows fly ash, which is made by substituting 20% of fly ash for moderate heat potent cement is used. And MF30 is 30% of fly ash. The replacement weight rate of fly ash used for dam concrete is ordinary 20% or 30% for Japanese dam. And air content and the slump is as shown you. And VC value is checked here. This slide shows the VC test, a method for evaluating the fresh property of RCD concrete. This test is arrangement of the VB test for RCD. Coarse aggregate for 40 millimeter or more is screened, and with a 20 kilogram weight on the top, vibrate the lower shaking table and measure the time it takes for the mortar to come up on this slit. The photo shows a situation where coarse aggregate of 40 millimeters or more is being screened. It's very hard work. At the construction site of the concrete dam, this work is done once every 1 to 2 hours for the quality control test to the dam concrete. And this slide shows the variation in the compressive strength of concrete in the outer part. Outer part. At 91 days with each, there is a variation of about 5 to 10 Newton per cubic meter, Newton per square millimeters. And this slide shows compressive strength improvement, increasing the compressive strength, and A and B2 compositions. The water cement ratio is 53%, about 53% and 75%. And the maximum size of gravel and cement, type of cement and slump and air content the same. It changed the only water percent ratio. Strengths are increased after 91 days, and the strengths increase more V2 compositions of strengths more increases than A.
Mr. Torichigai, sorry
Yes.
for disturbing. So you have 5 minutes.
Okay.
It's okay.
Okay.
Thank you. Please.
And this slide shows the compressive strength development of V1 RCD concrete. That's the sorry. That's similar to slump concrete. So to compressing strength increase after 91 days, and then I try to show the cement water ratio and relationship cement water ratio and increase in compressive strength for about 1 year and 2 years compared to 91 days of compressive strength. Cement water ratio and the long-term increase of compressive strength have high correlation. And here, the compressive strength of 2 years is twice compared to the about twice compared to the 91 days of compressive strength. Compressive strength of dam concrete using fly ash increases over several years, especially high cement water ratio. That's the conclusion of my presentation. In Japan, fly ash is used under the strictly controlled at the concrete dam. The amount of air content is kept constant by finally adjusting the amount. Finally adjusting the amount of air entering agent for each season and each day. The compressive strength of concrete using moderated fly ash cement increases over the long term. That's the end of my presentation. This photo shows the Gokayama Dam. I worked at this site, Fukuoka, Japan. Thank you for your kind attention. Thank you for listening. Thank you.
Thank you, Mr. Torichigai. Very nice presentation. And yeah, we are very happy to hear about some of the new technology about the dam construction using the fly ash. I think in Mongolia and also in Indonesia, the need for deal with fly ash, I think the need is high. So your presentation, I hope that will help for that technology advance in all of the countries. Thank you.
Thank you.
Okay, so we would like to proceed to the question and answering the session. I'm glad that we have already had a lot of questions, so I could just pick up some of the questions. So let's go from the order of our speakers. So first, the question go to Professor Han. So first is, if FRP is used to repair damaged concrete, so how can we control that the concrete is still under reinforced condition?
Thank you very much, Dr. Luan. To answer this question, indeed, we have to recalculate that even with the additional of the shear and the fractural reinforcement, we still have an under-reinforced condition, of course. Because what usually happens, if I'm talking about an already cracked section, there is a big possibility that the conventional reinforcement steel has already yielded. So by straightening the beam, actually you will create a strain in the opposite direction to the tensile strain in the steel. So this you have to keep in mind, and you have to add it into the calculation. So what we did is some kind of a post strain before strengthening, and then you have to recalculate again after applying the FRP that make sure that still the neutral axis will fall in this manner that the steel will yield before the concrete crushes. That is it, Dr. Luan.
Thank you for your answer. I hope that will very helpful the audience the answer as the understanding. Yeah, we have another question to you, that is regarding applying FRP to concrete structure for retrofitting. Do you have any experience to apply FRP to masonry, the structures for retrofitting?
Well, based on my experience, actually the wrap is the most easy part to use because it's very flexible and it's easy to apply. But the disadvantage of using a wrap is that it will create a lot of dust because you have to clean a very large area because it's a sheet. So you have to clean the whole area. And especially when we found out that the surface preparation as recommended by Sika was not good enough. So you have to create those grooves. It will cost a lot of time. It's very time consuming. It is very energy consuming. So from my point of view, I would like to use the rod. This is personally because that is the easiest one to apply. And as long as you have enough cover, you can plant it according to the ACI, then you actually have the best performance. That is it, Dr. Luan, and the person who asked the question. Thank you.
Yeah, thank you. And yeah, we have a lot of questions. And so maybe we have enough time this time for 30 minutes. So another question to Professor Han is, so do we need to consider the environmental conditions when we apply the FRP to structure? If we do so, what type of FRP that very suitable to apply to structures which exposed to the marine environment?
Thank you very much for the question. Actually, indeed, I already mentioned it before that if you lose the wrap and the plate, it'll create a lot of dust. And we were working in the lab for days and days, and everybody actually got very angry with me because the whole lab was polluted with the noise of grinding the concrete and all the dust that was created because I had to clean up the whole surface. So that's, of course, it's not very environmental friendly. Apart from that, the people were complaining about the noise, that because the grinding machine created a lot of noise. So if you and the other thing is it consumes a lot of epoxy for bonding because this one is impregnated in the field. So you need actually, so you should put the epoxy first on the concrete surface, then you have to put the wrap and then another layer of epoxy. But on the other hand, if you're using this rod or a plate, then it's already impregnated in the a factory. So when you come it, you only need the epoxy to attach it to the concrete. So in terms of environment, yeah, indeed, that is what I mentioned before. Then I will choose the rod or the string because they are both NSMs. Thank you.
Okay, thank you. So very nice answering. I think very clear.
Yeah, I know it. We have been doing it from 96 to 2016. So it's entering the 5th year now. So we did a lot actually. So it's nice, and I would love it if friends here attending would join the future research because we're still working on this, and it would be nice if I could have friends from other countries and from other university. I also just got a mail from Professor Weda Tamon. Are you still here, Professor Weda? He's attending, and
yeah,
I love his
I
good
think
friend
he's
of me.
attending,
Hi,
yeah.
Professor Weda Tamon. He's a very old friend of mine, and I'm very delighted that he's here to join us. Thank you, Luan.
Yeah, thank you. Thank you, Professor Han. So then I think that our next question goes to Professor Sagawa. So it's okay to you're available,
please
right?
go ahead.
So the question is, so you mentioned the GGBFS. In the recommendation there is a type, is a surface area is up to 8,000. The GGBFS 8,000 for precasting the concrete. So his question is, so he thinks that the biggest reason for using the mineral admixture is a slow hydration rate and low heat generation. But this is the 8,000 surface area, 8,000 square centimeter per gram. So when this finely powdered the mixture is used, so what it impact the hydration rate and hydration heat. So does it have any relation with the steam cooling? Because you also mentioned the precast concrete. Yeah, that's the question.
Okay. So this question includes many sub-questions.
Yeah,
Okay.
yeah,
Okay.
yeah.
So as I said, there are 4 types for GGBFS in the Japanese industrial standard related specific surface area, 3,000, 4,000, 6,000, 8,000. So the question is about, the first question is about 8,000, right?
Yeah.
Okay, so
8,000.
8,000 is very, very, very special, specific usage, utilization, especially for, how can I say, the architectural panel or and so on. So for the civil structure, we do not use 8,000 specific surface area. So mainly 3,000, 4,000, and 6,000. And almost of them, 4,000 is very common type of GGBSS for civil structures. Okay, so the next question is 3,000 GGBFS for the mass concrete. So as you can imagine, the specific surface area is small relatively, so the hydration speed is small. So the use of 3,000 type of slab can be used for mass concrete to reduce the hydration heat. So okay, so the last question, I think the precast concrete. So for the precast concrete, it is better to use 6,000 because the rotation of the foam in the factory is very critical. So the producer wants to demold, make a demolding in the 12 hours or 1 day. So the higher speed of hydration is required. So the 6,000 is better for precast concrete.
Thank you.
Is
So
it
you, thank you. You explain very clearly for different the specific surface area. That's like I think they have the different. They have their own advantage and disadvantage for the using.
Absolutely.
So yeah, and then another question is I think this is also from Indonesia. The previous one is from Mongolia. Another question is, so maybe it's related to Indonesia, the standard. So he or she asked is generally, so the previous study found that the replacing to 20% of the cement using the mineral or the mixture result in good concrete. I think maybe according to Indonesia, the standard. And he says this is maybe applies for mainly ordinary Portland cement. But how about if we use other type of the cement, like Portland composite cement? So how about the percentage of mineral at the mixture for those other type of the cement?
Okay, thank you very much. So actually, we do not have the specification about the composite cement. So yes, I know in Indonesia, the composite cement is very common type. So, but we do not have experience for the composite cement. But I show the ternary blend diagram. So the any kind, some kind of mixture is available. For example, slag cement plus fly ash or fly ash cement and blast furnace slag. But you have to check the quality of the concrete, not only fresh property and hardened property. So I think the higher content of admixture increase the shrinkage. So you have to control the shrinkage, drying shrinkage and autogenous shrinkage. Otherwise, crack will occur.
Yeah, thank you. And then another question is, so he asked why, so why is a mineral admixture, so can reduce the alkali silica reaction? So can you simply explain?
Yeah, simple question is so ASR alkali silica reaction produce the expansive alkali silica gel in the concrete after the chemical reaction of alkali and harmful aggregate. So when we use mineral admixture, so the composition of gel is different. So it is not, it does not show the expansive behavior. So it is a very simple mechanism. But it is very complex mechanism.
I think it's difficult to explain in just 1 or 2 minutes. But if our audience want to know the details, so he can ask you personally later.
Okay.
Thank you, Professor Sagawa. Then we would like to ask, the question goes to Professor Dr. Yani. So available? Are you available now?
Yes, I'm ready.
Yeah. So the first, there are several questions. So one is, I think they are very interested about the bacterial. So that is has already been done. A lot of the researchers are doing that. So the one question is, how long does it take the bacterial to repair concrete? So the time for it has the effect.
Okay, thank you very much, Luang Sang. Actually, my presentations today not talking about self-healing concrete, but I did have another result on using bacteria to heal the cracks in the concrete. Maybe the concentrations of bacteria we use for healing the cracks is not the same as the bacteria I explained today. We have to use maybe like 3 times or 4 times higher than, the amount of bacteria should be higher because of the calcium precipitations, and the healing process will take place in the speed recover other than only using a small amount of bacteria. And usually if we use like a 5 liter per cubic meter in this per cubic concrete, in this my presentation, I use only 400 milliliters. So it is a small amount, it's only a half liter. But for healing the cracks, we have to use like a 500 milliliter per cubic meter of the concrete. So it will heal the concrete cracks. It's not for the macro cracks, but for micro cracks, because bacteria is a micro and tiny material. We cannot give the responsibility to bacteria to heal the macro cracks.
I agree.
For the limitation is like a 0.3 millimeter for healing for about maybe like a 20 days to 2 months. So it will heal the cracks completely. But in the last my experiment, I conducted the monitoring for about like 100 days, and it heals completely.
Okay.
Thank you for the questions.
We hope that the bacteria can live longer. So if there are the crack occurs, so it can repair again.
Yeah, it is a very healthy bacteria. It has a very long life, even longer than our life. Even after the experiment, even after my retirement, the bacteria is still working, I think.
Exactly. So, and another question is for you is you mentioned in the nutrition, maybe nutrition. So you use ammonium carbonate. Is that a nutrition for bacteria, or it's used for activator for the concrete?
Okay, thank you very much. The bacteria, the Sporosarcina bacteria I use in my experiment is like the basic of the enzyme is ureatic. So we use like ammonia created from some, like how to say, sato in Japan, but it's
Yeah,
uh, it's like
gross.
a sugar.
Yeah, sugars,
The
gross.
local
Yeah.
sugar from plant, from the natural plant in Indonesia, brown sugar actually, and we created the the nutrition for bacteria, and then it should be ready for just add to the concrete, just like super plasticizer. But we need maybe like a small amount of water to dilute the bacteria and the nutrients to be added into the concrete, and it's already commercialized, so we can buy it in Indonesia.
Thank you. Yeah, quite a lot of questions for our speakers. So another question, maybe still for Dr. Yani, it's regarding the bacterial for concrete. So can you please explain what kind of method do you use in mixing the bacteria in concrete? So in other research, the audience, so he says that he noticed that other researchers, they seal the bacteria in the form of capsule to avoid the early interaction. So in your research, what kind of methodology do you use?
Thank you very much. It's very interesting questions. Of course, as I explained in my slide, that I use aerobic bacteria. So actually, we use the spore, not the bacteria, only the spore. And then we have to, we have to avoid the contact of the spore with the air. So because after it contact with the air, then it will grow. I mean the population will grow. It becomes mature, and then create a lot of bacteria, and then will consume up all the nutrients before it works. So it becomes like a bigger population and doesn't work for anything. So just before we need it, we just open the lid of the bottle and then just add it to the concrete. And we have to consider also about using the super plasticizer. So we need some time, we have to make it like a longer time for the bacteria, or we have to avoid the super plasticizer contact directly with bacteria. So if we put the bacteria first, and then we have to put the super plasticizer in the final casting.
Okay.
If we put the super plasticizer first, and then we put the bacteria in the final casting. So we need some time. Yes.
Okay, we need to avoid their
direct the direct contact with the super plasticizer.
Okay, thank you. And maybe the last one, though, I ask you now. So it's someone asked you why you use sodium hydroxide with 0.003 the M. So can we use a higher or lower one?
Okay, thank you very much. Actually, we have to adjust first the pH of the concrete. Actually, I already explained that 12.5 to 13 is the pH, the normal pH of the concrete. But by using fly ash and bottom mass, and also the additional of the bacteria that containing ammonia, so the pH of the concrete will decrease. So in order to keep the pH of the solutions, we have to increase a bit the pH of the concrete. For example, we adjust the pH of the fly ash first. If the fly ash, it is very simple experiment. We mix the fly ash with the water, and then the ratio is 1 fly ash and 4 water, and then we mix that, and we measure the pH. If the pH is lower than 10, and then we have to adjust. We put the sodium hydroxide flake, only small amount, only like a 1 gram or 1.5 gram, just to adjust that the pH will increase to 12 point something. Not too much, because if it is too much, and then it will damage all the. So just small amount. And
Okay.
also we have to check again the pH of the fly ash. It's very important. If the fly ash is already in the alkali conditions, I mean, it contains a lot of alkali and also some calcium exists in the fly ash. Maybe we just use small amount of sodium hydroxide on the concentration, maybe not 0.03, only 0.001, or even we don't use any sodium hydroxide to boosting the fly ash reactions. So just to help the pH balance in the concrete during the casting.
Okay. Okay. So fly ash also have the variation in pH.
Yes.
Okay.
So we have to check that first.
I see. Thank you. Thank you so much.
Welcome.
And then we have a question. So go to Mr. Torichigai. Is that okay?
Okay. Yes.
For you too?
Okay.
So you mentioned that you use a fly ash in dam construction for it can reduce the heat of hydration. So how did you measure the heat of the dam or the concrete?
Okay. Measure. How do I measure the
measure?
heat?
Yeah.
Okay. Yes. Thank you for the question. And so for can I share my slide again?
Sure.
Okay.
Please.
Okay. So I'm sorry, but I don't have enough time to introduce this data and heat data. So I reject the data to my presentation, but I take this data. This slide shows the adiabatic temperature rise of dam concrete we measured, and this is a relation between day and temperature. And use of fly ash reduces temperature rise. You mentioned it, and this red line is examination data, right? And blue line is regression data to apply to these equations. And this this is the black line shows the ML30 data. So in the regression equation, the temperature rise converged about 14 days, and in this test, the amount of cement and fly ash unit weight is 130 kilogram per cubic meter, and we used this RCD concrete. Unit weight of cement is like 130. The mixed proportion of the concrete of RCD is adiabatic temperature rise is like this. Then I think I find a contradiction. So as I explained before, compressive strength of dam concrete using fly ash increases over several years. I explained before, but the temperature rise of the concrete converges in about 14 days. That's a contradiction. So we try to real adiabatic temperature rise of dam concrete using this equipment, and heat insulating material is covered to the concrete, and we measure the heat. So that's the result of heat of the concrete. Compound heat insulation, and concrete temperature is kept high for more than 30 days. And we try to simulate some analysis, and we try to get the real adiabatic temperature rise. It seems to be this line like that. So thermoconcrete using fryers may keep to generate a little bit heat in the long term, we think. Is it okay?
Okay. Okay. So that means so the later edge. So maybe if we do the analysis, but compare with analysis, maybe there are more the heat increase.
More.
Later.
Yes.
Okay, that may be very important.
Yeah,
okay.
That's so. Thank you. Yes.
Thank you for the answer. And another question is, you use the AE amount.
Yes.
It changes every day, the amount. You said the reason is because of fly ash quality and the temperature. So, which one is more important to affect the temperature or quality?
Okay. So I think it outside temperature is more effective for. So just a moment, please. So can I share the slide again?
Okay, please.
Okay. Okay. You mentioned about this figure.
Yes.
So
yes.
And in the summer,
in
summer and heat, we use more AE agent, and at the winter we use less AE agent. I think so. The outside temperature is more important than the quality of fryers. I think so.
Okay.
Yes.
Thank you. I think so. Maybe our friends from Indonesia, they care more about the high temperature, and our friends from Mongolia, maybe they care for more in the low temperature. So your data is very helpful for both of them.
I think yes.
Okay. And so maybe we almost the time, but I saw some audience they'll raise their hand for want to ask a question, but then anyone who want to ask question if you want to ask, you can raise your hand here. But I saw some audience raise hand, but I missed that. So anybody want to ask question by raising hand? Okay. I think the Dr. Yuta Yamada. So he would like to ask question. So he's raising his hand. So can you ask question, Dr. Yamada? Is that okay? So can you hear? I see you are raising your hand. Can you hear me?
Okay, I hear.
Okay. Please, if you have any question.
Thank you. My question is for the Dr. Han. Thank you very much for interesting presentation. So my question is regarding to the pre-treatment difficulty about the pre-treatment method. And you presented the FRP load and the some fan shape of the FRP sheet method. I think that these methods are a better way to keep the ductility for the structural members. But I think it is a little bit difficult to apply for existing structure because pre-treatment method is difficult, a little bit complicated, and just my image. So could you tell me your opinion about that point?
Professor Han, your voice is mute.
Okay, thank you very much for the question. Yeah, you are correct because it's inside the room. So we have to evacuate the room first. And then we have to prepare the floor because actually the part in tension at the beam column joint is on the floor. So we have to evacuate the room, and the people living in the room, they cannot use it. Yeah, you're correct. Of course, it is disturbing, but I think it is always better than demolishing the building and needing to build a new one, because then you will running with the waste of the building. You have more cost to build a new one. So yeah, indeed, it is not the best solution, but it is better than having to build a new one.
Okay, thank you very much.
Okay, thank you. Thank you for Professor Han for your answering, and thank you for the question from Dr. Yamada. And
Yes,
any other question? Any ask question from our audience? Okay, so yeah, I think so. We are approaching the end of the seminar because it's already so the time the 12.
Luan-san, can I have a request to Sagawa Sensei?
Yes, please, please.
Okay. Yeah, actually, I want to know the recent development of research on geopolymer in Japan, because last time I worked with it is just not correlated with the with the topic of Sagawa Sensei. Yeah, I just want to know what is the situations and the current conditions on the geopolymer research in Japan. If it is possible, I would like to make more collaborations with Japanese friend on geopolymer, especially using fly ash and blast furnace like. Thank you, Luan-san.
Thank you.
Thank you very
Thank you,
much.
Yang-san.
Okay, so the current situation of the research of geopolymer. So as you know, currently there are so many research activities about geopolymer in the world. So I think, in my opinion, Japanese researchers started, I think, about 10 years ago. So, but the actual application is very small amount. For example, the precast block or slab concrete and so on. So we have just started to discuss. And as I said, we have the subcommittee about the geopolymer concrete and alkali activated slag concrete in the concrete committee of JSCE. So yes, we are welcome to do the collaborative research. Thank you very much.
Is that possible to become the member of geopolymer division of JSCE? Maybe perhaps in the future you can open a special external member for the geopolymer part.
Okay, thank you very much.
Yeah.
Thank you very much, Sagawa Sensei.
Okay.
It's good to strengthen the more collaboration between the three parties for the future work. I think that our audience, if you are interested for that, so you can tell us. Yeah. Because the time is approaching, so we would like to finally before the closing, we would like to invite Dr. Yani to address the closing remarks, because she and the group contribute a lot for organizing this seminar. So it's okay, Dr. Yani, for the closing the remarks. Could you please?
Yes, with my pleasure. Good afternoon, distinguished professor, presenters, moderators, and all participants. It is my the great pleasure for me and honor to see the outcomes of this two-day webinar online and to provide my closing remarks. On behalf of Institute Teknologi 10 November and FIB Indonesia as the host, I would like to thank our supports from JSCE, especially to Professor Hamada, to provide presenters from Japanese side. I would like to express our gratitude and appreciations to our presenters. For the first day, Professor Hikaru Nakamura from Nagoya University, Dr. Fadilah Muslim from FIB Indonesia, Yeah, she presented from Germany, and Mr. Toshimitsu Kobayashi from Shimizu Corporations, and Dr. Batmun Narantuya from MUST Mongolia, and yeah, Dr. Luan Yao from Saitama University. We did enjoy your presentations yesterday. I would like to thank all contributions today from Professor Han Aili, the President of FIB Indonesia, Dr. Yasutaka Sagawa from Kyushu University, and Mr. Takeshi Tochirigai from Kajima Corporations. Thank you for sharing your valuable experience. Special thanks to my best friend, Dr. Luan Yao, and also Dr. Niar, who have prepared this event very well. Being a moderator, operator, and everything, give all your time to make this event become very much successful. To all participants, your attendance, questions, advices to this event has been extremely valuable. I'm very much pleased to see that fruitful discussions today and yesterday and interactions that have advanced amongst the participant and presenter during the past 1.5 days. We have discussed a very important topic on recent advances and practice on concrete that may be expanded to better Asian concrete in the future. There are many challenges that we are still facing in the three countries that are developed towards more global discussions and collaborations to involve more Asian country to join us in the future. This was also mentioned by Dr. Sagawa in his presentations. We appreciate this event to give us more opportunities to learn in the first day, and more than 600 participants, I think, from 3 countries has been submitted their registrations. More than 200 yesterday joined the first day, and more than 200 joined today. Thank you to all operators who control the Zoom room and the live streaming event on YouTube very well. And thank you, Dr. Yuta Yamada, for your help. Finally, I wish you all good health and hope to see you again in the next JSCE webinar. On behalf of ITS as the host of this webinar, I would like to call the event to close. Terima kasih, Bayer Lala, arigatou gozaimashita. Thank you very much. And yeah, we go back to Luang-san.
Okay, thank you so much. Thank you, Dr. Yani, for very nice closing remarks. So we hope, like in the future, we still like next year and later we have more and more such kind of the communications and seminar and for more collaborations. Yeah.
Gambarimasu.
Gambarimasu. Okay, so our friends, our audience, if you have any more questions that not yet mentioned in the discussion, the group, the section, so you can directly let us know by sending email to the organizer. Okay, so yeah, we complete. So shall we take the like for
Sure.
each the
Yes.
Yeah, we can take a virtual picture, I think.
We have almost 200 participants here.
Yeah.
How many slides or how many? Yes.
Yeah.
Okay.
We take the virtual pictures. Okay, I think it's finished.
Okay.
Thank you very much.
Thank you very
Dr.
Thank you so
Luan.
much. Okay. Thank you. Thank you so much for our audience for attending here. So see you maybe next year. So bye-bye.
Bye-bye.
Bye.
Thank you very
Bye.
much.
Thank
you
you.
very much.
Thank you very much. Okay.
Hamada Sensei, thank you very much.
Thank you. ワン先生、ありがと
Yeah. With my
う。あり
pleasure.
がとうございました。 Thank you very much.
お疲れ様でした。
お疲れ様。
そうでした。
See you.